Hello everyone. Welcome to grade 12 physics. We're starting with Unit 1 Dynamics. Unit 1 is organized in 3 chapters. Chapter 1, Kinematics. Chapter 2, Dynamics. And Chapter 3, Uniform Circular Motion. You should be able to meet overall expectation and be introduced to big ideas in this unit. Chapter 1, Kinematics, includes all the knowledge that you already learned during the Unit 1 Kinematics in grade 11. After completing this chapter, you should be able to solve 1- and 2-dimensional motion problems involving average speed and average velocity, calculate average acceleration using a vector subtraction in 2 dimensions, solve a projectile motion and relative motion. Section 1.1 is about motions and graphs. So after completing this section, you should be able to understand types of motion and interpreting graphs. In order to understand the motion of the object and to understand any concept for that matter, we must first be able to describe it. So in order to understand motion, you should be able to describe motion. Kinematics is a term used by physicists and engineers, as you know, to describe the study of how object moves without getting involved why object moves in that way. So, kinematics is study of motion. What is motion? Motion is a change in location of the object from the reference point as measured by an observer. So, sometime or most of the time, an observer is just you, that you are describing that motion. So, reference point is a point used to find or describe the location of something, the location of the object that you are studying. Distance is a simple concept. The distance is a total length of path traveled by an object in motion. So the distance symbol is d, lowercase d, and a standard unit is meter. For example, what is the distance traveled by you if you start from your home, go to your friend's house, and then go to the grocery store? So you go from your house to your friend's house, you travel 2.1 kilometer, and then you go back another 2.1 kilometer, and then from your house to a grocery store, another 4.3 kilometer. So as we said, is a total length. So every motion in any direction counts as a distance travel. So we have 8.5 kilometer travel. It is a very important in physics understanding to be able to distinguish between scalar and vector quantities. A scalar quantity is a quantity that has a magnitude or a size only. For example, time or mass or height. So you never question that those quantities about any direction whatsoever. However, a vector quantity has a magnitude, also direction. So the direction is very important in a vector quantities. An arrow is placed above the symbol for a variable when it represents a vector quantity. We're going to learn about the vector quantities in this chapter. How to add vectors? In order to add vectors, we can place a tip to a tail of the other vectors. So we can place one vector after the other. Direction of the vectors does matter. So let's say that we have 2 vectors, A and B, and we have to add them up, making the sum of 2 vectors as a vector C. How can we draw it? Let's say that we draw vector A first, and that vector A has to be proportional to its magnitude. So, and then immediately after vector A, we draw vector B. So where the vector A ends, vector B starts. So the start of the vector is called tail, and end of the vector, where the arrow is called tip. So we are talking about we place the tail of the vector B to the tip of the vector A. That's why it's called tip to tail method. Then we can actually, in order to add those vectors together, we can draw another vector which is a sum or a total of the two vectors. Then that vector has to be starting where the first vector starts, in this case where the A vector starts, and should end where the last vector ends. So it's going to be tip of the vector B, like this. As a matter of fact, direction matters because it's not you are just adding two vectors together as a magnitude only, but direction does have to be very important. So if you want to add a vector A and you have another vector B which happen to be the opposite direction of the vector B that we just drawn before, in opposite direction like this. So the rule is the same. You place the tail of the vector B where the tip of the vector A is. With other words, we can say we can place the start of the vector B to where the vector A ends. So we can place vectors one after the other, and as a total would be again the same rule. Start where the first vector starts toward where the last vector ends. So where the tail of the vector A toward tip of the vector B. So if you see very clearly, vector C, which is a sum of vector A and vector B on both cases, is totally different. It's different because now we are adding vectors. We are not just adding numbers. So the length of vector represents its magnitude. That means by looking at those two vectors A and B, for example, we know for sure that magnitude of vector A is bigger than magnitude of vector B. Why? Because vector A is drawn longer than vector B, and we know the vector C is longer than both. Now if you see the diagram on the right, vector A is the biggest one, then vector B, and a sum of those two vectors is even smaller than themselves. So the magnitude is very important also, but the direction is determining that sum of those two vectors when we add vectors together. We can say, we're going to talk about this later on, we can say that in a second diagram, we can represent the second diagram as A minus B as well, because two vectors, we can label them as a vector A, for example, and vector minus A if they are at the same magnitude but at the opposite direction. In this case, vector B and minus B are drawn with a black on a first diagram and minus B on a second diagram. So direction does matter, and it produces a different result as different directions are applied. So it will be very helpful if you refresh your knowledge about vectors, and some knowledge are at the end of the textbook. You try to read those time after time. However, I'm going to try to explain in a very detail what you need to know about vectors. As we study vectors, and we use those vectors a lot in chapter 1, chapter 2, 3, and 4, so the first 2 units, and this is repeated on grade 12 as well. So direction matters. Direction is a very important component of the vector. So direction is the line an object moves along from a particular starting point expressed in a degree on a compass or in terms of the compass point, like north, west, east, or south. Sometimes we express a direction based on the expression that we use in everyday's conversation, like up, down, left, right, forward, backward, and even with a plus and minus with an x and y coordinate system. So directions are often expressed in a square bracket, and we're going to use square bracket all the time. For example, we can express 500 meters east, which indicate that object is moving 500 toward the east direction. Take a look on that compass there. There's a red arrow, which is a vector pointing toward east. And the length of the vector has to be proportional to magnitude, and we already talked about it in the previous slides. Why direction is important? Imagine if you have a phone conversation with your friend and you want to meet somewhere, and they ask you to meet 500 meters from the certain intersection. You go to that intersection, but you don't really know where to go. North of that intersection, south, east, or west. So you are going to take chances, right? If you don't have direction, you're going to take chances and you might go 500 meters north. You're going to look around. There's nothing there. Go back to the intersection again, 500 meter backward, and then may go 500 meter, east or west or south. Still you're taking chances until you get the right position. However, if they said that we're going to meet 500 meters west from that intersection, you don't have to think about north or east or south. You go directly to west and you meet that person. So that's why the direction is important. So if you want to go to school and you are in a library or from home, that means that school have a different position relative to your location. So if you are at home, your school is 500 meters east of your home. But if you are at the library, the same school is 700 meters west of your position, west of the library. So the motion toward the same object is described differently, which depends on from the reference point where you are located. So that makes a direction very important. We're going to learn about position and displacement. Position is a distance and direction of the object from a particular reference point. So position is like a location where the object is located. Position is a vector quantity because it has a magnitude and direction, and is represented by a symbol d, a lowercase d, with a vector on top. Please do not confuse that with a lowercase d for distance. Here is an example to make it clear. What is the position of the school and the position of the library shown in this diagram? Position of the school from the reference point, which is your home in this situation because it's a 0 meter, is a 500 meter if you walk toward east. So that's why it's 500 meter east. And a library is a 1200 meter east. So if you start from your home and you want to go to the library, you have to go toward east direction, and you can move 1,200 meter, 1200 meter toward east. So kinematics is about motion, study of motion. It's about moving the object. So we talk about position, which is a location where the object is located. Now, what about changing to that location? What about moving from one position to another? So that's why we study displacement. The concept of displacement is the net change in position. The symbol is delta D, which is equal final position minus initial position. Let's do an example. You see that person there? It's starting from the position which is initially at 11 meter west to a 22 meter east. So find the displacement when initial is 11 meter west, final 22 meter east. We can just use that formula. Delta D is equal D final minus D initial is equal 22 meter east minus 11 meter west. We have a problem here because we do have two directions that are not the same. So what we need to do is flip one of them to make it the same. Either we can make two directions, both of those directions east, or both of those directions west. In order to switch the direction, we at the same time we flip the sign in front of that magnitude on that number. So 22 meter east, in order to make it to 22 meter west, we can switch it to a minus 22 meter west. And 11 meter west, if you want to flip it to make it 11 meter east, so we can switch from minus 11 to a plus 11 east. And it will make more sense to change negative to positive. So that's what we do. We change 22 meter, we leave 22 meter east, and we change it 11 meter west to a 11 meter east by changing the sign minus to plus. So now we are ready to add them up. 22 meter east plus 11 meter east is 33 meter east. Here is an example. We have initial position 500 meter east, which is school, and final position 1200 meter east, which is library. So when we go from school to library, what is the displacement? Okay, so we do the same thing. Delta D is equal D final minus D initial. D final is 1200 meter east minus 500 meter east. Since that both directions are the same, we just quickly do 1200 meter minus 500 meter is a 700 meter east. When an object changes its position more than once, experiences two or more displacement. The total displacement of the object can be calculated by adding the displacement using the following equation. Delta D total is equal to delta D1 plus delta D2 plus delta D3, etc. Here's an example. A student walks from her home to her school and then to the library. Find the total displacement. So we have two displacement, and we can calculate displacement for each individual trip. So delta D1, which is final position of the segment 1 or trip 1, minus initial position of trip 1, plus final position of trip 2, minus initial position of trip 2. So we have 500 east minus 0 meter plus 1200 meter east minus 500 meter east. So if you see the 500 meter east and minus 500 meter east cancel, and we're left with 1200 meter east. However, total displacement can be calculated just a difference in position of the end minus position of start. So no matter where you go through many trips, what matters is where did you start and where did you end up. So where is the end position of the object and minus start position of the object. To make it clear, so when you start in the morning from your home, you go anywhere during the day. However, at the evening, you go home again. So you start and end that displacement, that many trips during the day to the same position. So that means total displacement for the day is end position, which is a home, minus start position, which is home. So that's why total displacement for entire day for you that's starting from home and ending up at home is 0. So that actually is a wake-up call for you to understand that displacement is not about how long you are traveling. It's about change in position. Start position, end position, those two are what matters. Now, if we have to review back, what is a distance is a total length of path traveled. Now, displacement is about start and end, change in position. So here is an example. A student walks from her home to her friend's house and then to a grocery store. Find the total distance traveled. So if you see that total distance travel matters any direction that you go. 2.1 plus 2.1 plus 4.3 is 8.5 kilometers. Now the same example is to calculate displacement. So a student walked from her house to a friend's house, then back to a grocery store. That means it goes from your house, from her house, to a friend's house, back to the house, back to and toward grocery store. So we have 3 trips there. So one is a negative 2.1 because it goes from your house to a friend's house, opposite direction of the positive. And then from a friend's house to your house, that's another 2.1 kilometer, but this time is a positive direction because it is the direction that we have here, a positive direction. And then from house to a grocery store, that would be a positive 4.3 as well. If you see a 2.1 and minus 2.1 and plus 2.1 will cancel each other. So what is left is plus 4.3 kilometer. However, if you take a look, where did you start and where did you end up? You start from your house and you ended up to a grocery store. So that means final position minus initial position for entire trip. That means is 4.3 kilometer. So just to summarize, total displacement for that entire trip is 8.5 kilometer. However, displacement is plus 4.3 kilometer. So you can try yourself now. You can pause the video and try to calculate total displacement and total distance. So a student walks from her house to a grocery store and then to a friend's house. Find the total displacement and total distance. You can pause the video and try it yourself. Then, if you get the total displacement of minus 2.1 and total distance of 10.7 kilometer, then you understand the concept. Now, as we already mentioned, the distance depends on a path taken, so every meter counts. So distance is a scalar quantity, the direction doesn't matter. The displacement does not depend on a path taken, but is just 2 points. There's a change in that position from final minus initial. So the direction of that displacement is from initial to final. That's why it's a vector quantity. So it's a vector that joins start toward end. Now, magnitude of displacement, since that is a straight line, is always equal or less than a distance. There is no way that magnitude of displacement can be longer than a distance. So we can say absolute value of displacement is always less than equal than distance. Now, I label distance as a delta D. The reason that I label that as a delta D and not D is that sometimes we interchangeably use displacement and distance if there's a straight line, if the motion is in a straight line and we know the direction, or the direction is already understood. For example, when we solve physics problems that involve, for example, car driving, we know that usually car drives forward. So we don't really need to mention it. Instead of saying displacement, we say distance or vice versa. So we know exactly what we mean. We know exactly that if the car is moving 5 kilometers toward east, that is a distance 5 kilometers because that was a straight line. Here's another example. You can pause the video and you can try it yourself. If you were to walk from home to work, what would be your displacement? So the work position is 2,000 meters west, and your home is the reference point is 0 meter. So we can do the same thing as we did before. Change in position is final minus initial. So that means 2,000 is a final where you ended up. West minus 0 is 2,000 meters west. Second one, what is your displacement if you walk from school to the market? So you start from school, which is 700 meters east, and you ended up 2,500 meters east. So you do the same. 2,500 meters east minus 750 meters east is equal 1,750 meters east. One more. You have to go to a market one evening after work. What is your displacement from work to market? From work to market. So end position is market, start position is work. Same thing, final minus initial. Final is market, which is 25 meters east minus 200 meters west. That will make, so again, we have a east and west. We have to change west to east, and that negative sign in front of 2,000 will become positive sign. So 2,500 meters east plus 2,000 meters east is 4,500 meters east. Next one. After school, you have to go to the market before returning home. What is your total displacement? Okay, same thing all over again, final minus initial. So final you returned at home, that will be 0. Minus 750 meters east, that is equal minus 750 meters east. However, write it down, we cannot leave the answer with a negative. So what do? We flip it, flip the direction, and we flip the sign from negative to positive. So the answer will be 750 meters west. Average speed versus average velocity. The average speed is a total distance traveled divided by total time taken to travel that distance. So since the distance is a scalar quantity, speed is a scalar quantity. The formula is V average is equal to delta D, which is a distance over interval of time. Unit is meter per second. Remember, not kilometer per hour, meter per second. Average velocity of an object in motion is its total displacement or change in position divided by total time taken for that motion. Velocity describes change in position over time. So since the change in position or displacement is a vector quantity, velocity is a vector quantity. The formula is similar to that above. V average is equal change in position over interval of time. Unit is meter per second, but since that is a vector quantity, has to be associated with direction. Now take a look on the diagrams on the left. There's a car, same car, moving left and right. The speed in any direction, since that is a scalar quantity, is the same. It's at 25 meters per second. However, direction matters at velocity. So traditionally, right direction is positive and left is negative. So that's why velocity on a car that is driving on a right is plus 25 meters per second, and velocity of the car that is driving on a left is minus 25 meters per second. Another consideration that you need to know is that since the speed and velocity has to do with a distance and displacement, they are not the same. They are the same if that motion is in a straight line in one direction, same direction. However, since that for a distance every meter counts, so path taken by an object matters. So distance is always different. It's bigger or equal than displacement. Here are some practice using average speed. A baseball roll along a flat parking lot in a straight line at a constant speed of 3.8 meters per second. How far will a baseball roll in 15 seconds? So what is given? Average speed is given and it is in a standard unit. Time is given and it is in a standard unit. Distance is required. We can use a formula, solve for delta D for distance, plug numbers, and then answer is 57 meters. A paper airplane flies 3.7 meters in 1.8 seconds. What is the airplane average speed? Same thing. What is given? Make sure they are in a standard unit. They are. And what is required is an average speed. Make sure you use proper symbols to write what is given, what is required, because when you're using formula, then you are using those symbols in the formula. So V average is distance over time. It's a 3.7 meter over 1.8 second. The answer is 2.06 meter per second. A cheetah can run at a maximum speed of 30 kilometers per hour. How far can the cheetah run at 3.27 seconds? So what is given? It's given a V average 30 kilometers per hour. However, that is not a standard unit. In order to convert it in a standard unit, you have to divide it with 3.6 kilometers per hour over meter per second, which is 8.33 meter per second. Time is given and it is in a standard unit. Distance is required. So we can use the same thing, use a formula, solve for distance, and then you have a standard unit of distance 27.2 meter. So again, it's very important to use standard unit because the answer has to be in a standard unit as well. I already mentioned where this number 3.6 came from. It is about kilometer. It is a 1,000 meter, and 1 hour is 3,600 seconds. So it's a 1,000 over 3,600. That means it's 1 over 3.6. So that's why you use dividing by 3.6 to convert kilometers per hour into a meter per second. Let's do some practice with the average velocity. If you see a sprinter goes from 0 to 50 meter running, and then from 50 meter goes back to a 0 walking. The first sprint section or run section is 8 seconds, and the other one, return or walking section, is 40 seconds. So total is 48 seconds. So what it's looking for is the average velocity for first section, run, and then second section, which is walk, and then entire trip. We can just mark the positive direction. It is on the right, and you take a look on the arrow there. So the arrow here shows you the positive direction of the x-axis. Okay, so let's start with the run section. Again, it's a displacement over time. The displacement is a change in position. So how the position changed? From final position minus initial. Final is 50 meter, initial is at 0 meter, over final minus initial time. So it started at the 0 second, obviously, and it took 8 seconds to go to a 50 meter sign. So it's a 50 minus 0, 8 minus 0, that is plus 6.25 meter per second. On a return section, you go from a 50 to 0. So 0 is a final, so 0 minus 50, divided by, and it takes 40 seconds. So total is 48 seconds minus 8 is 40. And the answer is minus 1.25 meter per second. And makes sense. So if you see the arrow on a walk, under the walk, it is opposite direction of the positive direction, which is, that is -1. And is expected to be negative. For an entire trip, you started at 0, you ended up at 0, so that means 0 minus 0 is 0, divided by the entire trip was 48 seconds, lasted 48 seconds. So 48 minus 0 is 48, but 0 divided by any number is going to be 0 anyways. So the average velocity is 0 because change in position or displacement is 0. So that is a learning opportunity here, that yes, although you are moving, average velocity can be 0, which in a normal way of thinking, you cannot think that speed can be 0, but velocity can. Some more practice with the average velocity. On a windy day, a position of the balloon changes as it blows 82 meters north away from a child in 15 seconds. What is the average velocity of the balloon? Again, what is given, what is required? Make sure that all of them are in a standard unit, and then write the formula and plug in numbers. So it's 82 meters north divided by 15 seconds. It is a 5.5 meter per second north. So obviously the direction of that velocity comes from direction of change in position or displacement. Next one is a subway train travels at the average velocity of 22.3 kilometers per hour west. How long will it take for the subway train to undergo a displacement of 241 meters? What is given, what is required? Just write it there on the top left corner. Displacement is 241 meters west. Average velocity is 22.3 kilometers per hour west, and time is required. Thing is, we have a problem here. Average velocity is not in a standard unit, so that's why you can change it to meter per second. So 1 kilometer is a 1,000 meter, and 1 hour is a 3,600 second. So it is pretty much ended up to a divide 22.3 with 3.6. So that's why that 3.6 came from. And the answer is 6.19 meter per second west. Now we are ready to solve for time. Time is delta D over V average. You can plug numbers now. You're ready. All are in a standard unit. So if you see that the west and west cancel, the direction cancel because the time is a scalar quantity, and you have 38.9 seconds. When we compare average speed and average velocity, we have to take into consideration what they are equal to. So they depend on, average speed depends on a distance, and average velocity depends on a change in position or displacement. So the magnitude of average velocity of an object is always equal or less than average speed. So when they are equal, when it's a straight line in one direction. So let's compare that section that we did already before from a 0 to a 50. For a sprint section, the average velocity was plus 6.25, but since that we are talking about magnitude only without considering sign at all, so now we can say magnitude of average velocity is 6.25 and average speed is 6.25. Now for the second section, remember that the average velocity for a walk section was minus 1.25, but now we are talking about magnitude only. So the magnitude of average velocity for a walk section is 1.25, so is average speed. However, so that means that the magnitude of velocity is equal to average speed. So when we compare now in a round trip, so when is the direction does change for the entire trip, things are different. And that's what you see, that average velocity for an entire trip, which we did already calculated before, is 0 divided by 48 because of the magnitude of displacement is 0. So that means that magnitude of average velocity is 0. But average speed is not, because in an average speed, distance is considered, and a distance, every meter counts, no matter what direction. So we have a 50 meter in a positive direction and a 50 meter on a negative direction, although in a displacement is 0, in a distance is just simple addition of 50 plus 50, 100 meter. So the average velocity is 0, but average speed is 2.08 meter per second. And obviously 0 is less than 2.08, so we came to a conclusion that we had that before, that average velocity, magnitude of average velocity is equal or less, and that is example for less than average speed. Now we are going to talk about position time graph. So graph and slope we learned already in grade 9, so the prior knowledge would be very useful here. However, you can start learning anytime. A position time graph is a graph that describes the motion of the object with a position on a vertical axis, traditionally was y-axis in a grade 9 math, and a time on a horizontal axis, which is x-axis on a xy coordinate system. For now, in physics, we use position time graph. The slope of the position time graph gives the velocity of the object. So slope is a rise over run. So what do? We do a change in a y-axis, which now is a change in position, over change in an x-axis, which now is a change in time or interval of time. So basically it's a change in position over time. That is slope, and that is average velocity. We should be able to interpret the motion just by looking at the graph. So here is a one-dimensional graph, which is telling us that at a time 0, when it starts, the object was at a 1 meter from a reference point, and it moves at a positive direction to a 3 meter on another second, and then from 3 to 4 in a time 2 second, and on a time 3 second went back to a 2 meter from a reference point, and then on a 4th second time it went to a minus 1 meter. That means in opposite side of the reference point, 1 meter from a reference point, but in opposite side. So yes, we can understand that, but the best way to actually draw a graph is what we already are used to. We're used to this space and time graph. It's very clear in this graph that yes, when time was 0, the position was at a +1. At a time 1, it was a +3. Time 2, it was a +4. Then on a time 3 second, went back toward the reference point, and then somewhere 3.6 or 3.7 crosses the reference point, and on a 4 second time it went to an opposite side of the reference point at 1 meter away from reference point, but on a negative side. So now we have a space-time and we can analyze it. We can use this graph to calculate average speed. So yes, it is useful, the graph on the left is useful to count what distance that object traveled. For example, from time 0 to 1, it travels 2 meters. So from 1 to 2 to 3. And then from 1 second to 2 seconds, it travels another meter, which makes 3. And another second, it travels 2 meters, which is from 4 to 3 to 2. And then from 3 seconds to 4 seconds, it travels 3 meters. So 2, 1, 0, -1. So it's 8 meters per 4 seconds. We know average speed is 2 meters per second. Now for average velocity, it is much easier with the graph on the right, because the average velocity is about where did you start and where did you end up. So you started at the +1 and you ended up at a -1. So it is a final minus initial. So final is -1 minus initial, which is minus +1. So it's a -1 minus +1, which makes -2, divided by 4 is minus 0.5 meter per second. And that is a slope that can, if you join 1.1 and -1 on that graph with a line, that is the slope of that line, which is a negative 0.5. Now, how can we build the graph? We learned about building a graph in grade 9. However, now we have a slightly different with a graph that we are used to with the x and y. Now we have position time graph. When a motion involves constant velocity, the displacement is the same during equal time intervals. So that is the easier one, which results in a straight line. So it's a linear one. So when we build a position time graph, and we can derive velocity time graph from it, one thing that we have to take into consideration is the same motion. It's an object moving. It's about one object that is moving, and we analyze the same motion in two graphs, position time graph and velocity time graph. So here is a table of data. If you take a look, it's a time from 0 to 8 seconds. So when you build time, which is a horizontal line, horizontal axis, we have to label that from 0 to 8, not less, but not much more. You can label it up to 10 if you want, but not less than 8. When we draw and label vertical axis, which is a position axis, if you see the numbers there, it's a 0 to 144. You can label that axis with 0 to 144, or maybe a little bit more, 150, but not too much, not a big number, because you're not going to use that space of the graph, but definitely not less than 144, because we cannot plot a last point. So you have to be careful when you label it 0 to 8 or 0 to 10 if you want, and 0 to 144 or 150. That would be reasonable, actually, labeling on y-axis. Make sure the x-axis, or a time axis in this case, and vertical axis or position axis have nothing to do with each other. So if you see the scale was 0 to 2, 2 to 4 are equally, but has nothing to do with a 0 to 50 or 50 to 100 or 100 to 150. So they are totally independent scale for each axis. Now, what we do, we plot values. You see that you have 0 and 0 here, and we can put 0. And then we have 2 and 36. At a 2, we have 36. And at a 4, we have 72. And a 6, you have 108, etc., etc. So we draw a line that joins those points, and you take a look of the line itself. The steeper the line, the greater the slope, the greater the object displacement for a given time, which means the faster velocity, the higher velocity. So steepness of that graph is related to average velocity. So then we can use that line to calculate the slope of that line in order to build a velocity time graph. So slope of that line, which is a constant, represent velocity of the time. And you know already about how to calculate the slope and how to describe that graph. So that's how you build a velocity time graph. Again, one thing that I'm going to emphasize it again. Take a look of the time axis for position time graph, and take a look of the time axis on a velocity time graph. They match exactly. They have to be the same because it is the same object moving. Now you're describing it with a position time graph or velocity time graph, but time is the same. Another thing that I have seen people actually making mistake over time is that in a position time graph, you see a line that goes from 0 to a certain value. That is a straight line, and slope of the straight line is a constant. And when you calculate the constant, that has to be horizontal. Horizontal, not starting from 0. It has to be horizontal because that slope is equally everywhere that you can measure. If you pick 2 points from 0 to 2 or from 2 to 4 or from 2 to 8, slope has to give the same number because the slope of the straight line is the same. There are two types of motions, uniform and non-uniform motion. Motion with a uniform or a constant velocity is a motion at a constant speed, so magnitude, and in a straight line, so the same direction. So there are two components of velocity, magnitude and a direction. So both of them has to be the same, has to be constant. Motion with non-uniform velocity is a motion that is not at a constant speed and not in a straight line. So that means if the magnitude, direction, or both are changing, then the motion is non-uniform motion. Let me give you an example. If you drive in a highway, for example, and you put the car in a cruise control, and the highway is not always straight, it turns a curve. Now the speed is constant, so the magnitude is constant. However, direction changes. So that means that you are not traveling at a uniform motion, but you are accelerating. Now in a chapter 3, in a unit 2, we're going to learn how that is felt. How do you know that is accelerated motion? You're going to feel the inertia. You're going to feel your body is going to lean to the direction that we're supposed to be at the beginning before you turn. So that's how you feel inertia. That's how you know that you are accelerating. More about this you're going to learn in the future, but just to give you a heads up that non-uniform motion has to be with a magnitude, direction, and or both. One of those or both are changing, then there's no constant anymore. Is a non-uniform motion, which is accelerated motion. So we are going to study only motion with a uniform acceleration, or as we call it, uniformly accelerated motion, when an acceleration is constant. When acceleration is not constant, it's so difficult to use any formula, or you can use graph to analyze it, but it is very difficult to analyze that non-uniform accelerated motion, which is very complex. Keep it simple. We are talking about uniform motion and uniformly accelerated motion. Build a velocity time from a position time graph. Here's a practice, and there is a position time graph given. It's very clear that there are 3 segments on that graph, from 0 to 3, from 3 to 5, and from 5 to 6. And what we do, we calculate the slope of the position time line or segment, and we can build a velocity time graph right below. Remember, the time has to be the same, has to match, because it is the same motion described in 2 different graphs. So then we have a segment, the first segment, we get 2 points there, and we calculate the slope. The slope for 1 to 3 is, again, rise over run, or change in position over change in interval of time. So interval of time is 3 minus 0, and position is 15 minus 0. So as I said, you have to write a 0, although that doesn't change anything on calculation, because slope is about change. So change in a position over change in interval of time. So slope is a 5 meters per second. It's a positive. The second interval is from 3 to 5. Then we do the same thing, although as you practice, sometime you will realize right away that that slope is 0. So slope of the horizontal line is 0 because nothing changing on a y-axis. So 15 minus 15 is 0, and if you divide 0 with any number, that will give you 0 anyways. And the third one, from 5 to 6, you do the same thing. Change in position divided by interval of time. So final one is 0 and initial is 15, so 0 minus 15 divided by 6 minus 5, that will give you minus 15 meters per second. Then what do we draw? We draw a velocity time graph. We have to make sure that time has to match with that above graph, has to match. Then you can take into consideration that positive value are up to 5, but the negative value is up to negative 15. So when you draw x-axis or a time axis, you have to take into consideration the space. And it's very clear there. I left 1 quadrant for top and 3 on the bottom. Then interval is 0 to 3, correct? It's a constant slope from 0 to 3. So the constant value is graphed with a horizontal line for that segment from 0 to 3. Now, segment number 2 is 0. So that means from 3 to 5 has to be 0. Horizontal, 0. And then segment number 3 from 5 to 6 is minus 15 and has to be underneath at minus 15. And that is the graph. And here is a challenge of the day. It is calculating average speed and average velocity. Let's start with a problem. A car travels uphill at a constant speed of 35 kilometers per hour and return downhill at a constant speed of 65 kilometers per hour. What is average speed of the round trip? I have to warn you that answer is not 50 kilometers per hour. It is less. And the next one is, what is the average velocity of the round trip? B is not really challenging because that is easy, but I want to challenge you by calculating the average speed of the round trip. So uphill and downhill, and you don't really know the distance. So you're going to figure out that distance you don't really need. See you next time. Any change in object speed, magnitude, direction, or both means change in velocity, means change in motion. This change in velocity is called accelerated motion. Acceleration describes how quickly an object velocity changes over time, or the rate of change of velocity. So for example, if you want to compare a car that is accelerating faster or slow, is how quick the car picks up the speed for a shortest period of time. That means that car is powerful, is fast, is accelerating quicker. Take a look on the diagram on the bottom right. It's a velocity time graph, and you see there are 3 graphs there. One is steeper than the other. So that means A is steeper than B, and B is steeper than C. So the slope of that line represents average acceleration. That means that the object A is accelerating faster. That means it's picking up speed faster than vector B, than object B, and object B is accelerating faster than object C. So the formula of the average acceleration is AV is equal to delta V over delta T. So delta V is a change in velocity, and always change is about difference between V final minus V initial for interval of time. So average acceleration is going to be bigger if change in an initial and final velocity would be bigger, or interval of that change is going to be smaller. And this formula is one of the two most important formulas in kinematics. Here's some practice with the average acceleration. The velocity of the pack changes from 8 meters per second north to a 10 meters per second south over a time interval of 0.050 seconds. What is acceleration of the pack? So what is given? Its V initial is 8 meters per second north, and V final is 10 meters per second south. Interval of time is 0.050, and average acceleration is required. So formula is average acceleration is equal V final minus V initial over delta t, and we can plug numbers there. So V final is 10 meters per second south, V initial is 8 meters per second north, and interval of time is 0.050. We have a problem here because you have a south and north in the same equation. So we cannot do a mathematical calculation unless directions are the same. So that's why we flip one of them. It will make more sense to flip north to south because it has a negative in front. So when you flip the direction, the sign in front has to change as well. So that's what we do. Now we have 18 meters per second south over 0.0 over 0.50 second. That is equal to 360 meters per second square south. A race car is initially traveling at a constant speed when it begins to accelerate uniformly at a rate of 3.8 meters per second square backward. If after acceleration for 2.6 seconds, it now has a velocity of 137 kilometers per hour forward, what was the car initial velocity? So again, what is given and what is required? Average acceleration is 3.8 meters per second backward. So we can definitely use backward as a negative and forward as a positive, and we can convert it back at the end. This is for simplicity instead of using a big word on an equation. Interval of time is 2.6 seconds. Final velocity is 1.37 kilometers per hour forward, so that means plus 137 kilometers per hour, and initial velocity is required. So first we have to convert it to a standard unit because we're going to use those in an equation. V final is plus 137 kilometers per hour divided by 3.6 meters per second per kilometers per hour. That is 38.1 meters per second. Then we're ready to find initial velocity, which is V final minus A average delta t. Now we can plug numbers. Its initial velocity is 38.1 meters per second minus 3.8 meters per second square times 2.6. That is equal to 47.98 meters per second. So that's positive, so that means it's forward. If you want to convert it back to a kilometers per hour, now we have to multiply it by 3.6. But most of the time, you might not need to. If you remember, we studied acceleration using position time graph. So slope of the position time graph represents average velocity. Now we can study acceleration using velocity time graph. So they are similar with a time on a horizontal axis, but we have a velocity now on a vertical axis instead of position. The slope of the velocity time graph gives you average acceleration. So slope, which is a rise over run, is a change in velocity per interval of time. Here's an example. What is acceleration of the skateboard in a motion between 0 to 10? So you have 2 points there, interval of time is 0 to 10. Find the values of those 2 points. From a 0 second, the value of velocity is 0, and for 10 second, value is 30. So slope is a change in those values. So that's 30 minus 0 divided by 10 minus 0. Remember that. When you're going to do a slope, you have to write 4 points. Remember when you learn slope in a grade 9, it is y2 minus y1 over x2 minus x1. So has to be v final minus v initial over t final minus t initial. In this time, zeros do not make any difference, but you have to write it anyways because next time those 2 points might not be 0 and will make a difference. So average acceleration for this example is 3 meters per second square south. We can use velocity time graph to calculate displacement. For example, what is displacement of the skateboard in a motion between 0 to 10? The graph there is very simple graph. So we can calculate area under the line using the triangle area, which is base times height divided by 2. The base is 10 seconds, height is 30 meters per second. Then we can have 150 meters south. If you see the velocity label is south. For a complex, we can add areas under the graph for a known geometric figures. For example, you can split that into areas of the triangle and rectangle. You can calculate it as area 1 of the triangle, which is 25 meters per second, base times height divided by 2, and area of the rectangle, which is 5 times 10, 50. And then you can add those together and we have answer 75 meters south. If we have a table of values for a time and velocity, we can build a velocity time graph. So on a horizontal axis, we have time, and on a vertical axis, we have velocity. So here is table of data from 0 to 4 seconds and from 0 to 24. Again, when you draw a graph, make sure that you label the x-axis or a time axis to a 4 or closer to that number, but not less. Same thing for velocity. You can label it to up to 24, but not less. Here is how we draw it. So 0, 0, 1, 6, 2, 12, 3, 18, 4, 24. And if you have another one from 0 to 4, similar, but values of velocity are dropping. So then from 0 is 24, first second is 18, 2 second is 12, 3 second is 6, and 4 second is 0. So after you have those graphs, you easily can calculate the slope of that line that represent acceleration. So by looking at that line that goes upward, that means the slope of that line on a first graph would be positive, and a slope of the line on a second graph would be negative. So we can use slope as a rise over run or change in velocity per interval of time, which represent average acceleration. If you have noticed the speedometer in your car, it shows the speed at every moment. So instantaneous speed is a speed at a specific instant in time or at that moment. It is a scalar quantity as speed, and the symbol is just simple, v. So you can calculate using a limits. So instantaneous speed is a limit where the time goes to 0. So very, very small interval of time of delta d over delta t, which is a distance over time. The same way you can calculate instantaneous velocity, which is a velocity at a specific instant in time or a moment. It is a vector quantity because the velocity is a vector quantity, and symbol is v with arrow on top. So we can calculate the value of the instantaneous velocity when delta t goes to 0. That means that for a very small interval of time of displacement over interval of time. And the same way we can calculate instantaneous acceleration, which is the acceleration at a particular instant or moment, which is a vector quantity as acceleration, and symbol is a with arrow on the top. So this means that we evaluate the average speed or velocity or acceleration over a shorter and shorter period of time. As the time becomes infinitely small, we have instantaneous speed or instantaneous velocity or instantaneous acceleration. We can use a graph to calculate instantaneous velocity if there's a position time graph, or if there's a velocity time graph, we can calculate instantaneous acceleration if at any point, if we draw a tangent at that line. So the instantaneous velocity or acceleration is a slope of that tangent line. So that's how you draw a line. That line touches the graph at one point only. As average has to join 2 points in a graph, average between 2 points, the average in the interval of time of those 2 points. As you move closer and closer to the interval of time, then that average becomes a tangent on a certain point. So make sure that the tangent does not cut the graph. It touches the graph in 1 point only. By looking at the position time graph, you can determine what time of motion you are talking about, what type of velocity you are talking about. If the line is a straight line in a position time graph, so the slope is going to be a constant, that slope represents velocity. So what we are talking about, it is a motion with a constant velocity or a uniform motion. If in a position time graph, if the tangent changes, so that means if the instantaneous velocity changes, that means it is an accelerated motion. So change in velocity means there is acceleration. That means it's an accelerated motion. Here is a practice of solving problems. A train moving in a straight line with an initial velocity of 0.5 meter per second accelerates at 2 meter per second square for 2 seconds. It continues from 0 acceleration for 3 seconds and then accelerate with negative acceleration, slows down with 1.5 meter per second square for 1 second. So what we are looking here are those segments. From 0 to 2 is accelerating with a 0.5 meter per second, then is not accelerating at all for 2 to 5 for 3 seconds, and then is slowing down for 1 second, 5 to 6. So what is looking here is final velocity of train after 6 seconds. So there are 3 changes, and we can calculate final velocity separately for each segment, or we can just calculate as a change in velocity. So what do we have as a given? We have initial velocity of 0.5 meter per second. Then acceleration 2 meter per second square for 2 seconds. And then 0 for another 3 seconds. And then minus 1.5 for 1 second. What is final velocity? The formula is initial plus change in velocity. So change in the velocity is a delta t. But that changed 3 times, 3 segments, different segments with a 3 different interval of time. So we can do the same thing by now replacing those symbols with the numbers that we have, the given values. So V initial is 0.5 meter per second. Then A1, acceleration on segment 1 is 2 meter per second square for 2 seconds, delta T1, plus 0 meter per second, which is A2, times 3 second, plus minus 1.5 meter per second for 1 second. And then you get 3 meter per second. Now, if you take a look on the graph itself, it is very clear that that final is exactly 3 meter per second. However, I'm going to warn you something. You have a graph and you have the problem, word problem with values. You're not going to have that often, graph and values. The graph here is just to give you an idea that how that motion is. How can you understand better? But obviously has to be one or the other most of the time. So B is asking for average acceleration of the train. So let's get those 2 points that you can calculate the final and initial velocity for final and initial time. So initial velocity is 0.5 for initial time 0, and final velocity is 3 meter per second for time, which is 6 seconds. And then you can calculate average acceleration as a v final minus v initial over t final minus t initial, which actually is a slope of that line. Then you can plug those numbers and you get the average acceleration is 0.42 meter per second. Now, in this diagram might look a little bit complex, but is the connection between a direction of the acceleration and a direction of the initial velocity. So how do you know what is going to happen? How is connected? So if you take a look, there is a initial velocity here is bigger than final. So it's going to get smaller. So if the final velocity gets smaller, that means that it's slowing down. So what does it mean? When it slows down, then the acceleration has to goes against initial velocity. So if initial velocity is positive and slowing down, then acceleration has to be negative. Now, for if this car turns curve, then acceleration that we're going to learn in grade 12 is directed toward center of that circle, of that curve. That car is going through that circular motion. More about this in grade 12, chapter 3. But for now, what about when it speeds up? So that means that acceleration has to be at the same direction as initial velocity. So it is helping initial velocity to become bigger, faster. So it is like when you push the gas, that acceleration is in same direction as initial velocity, it's going to speed up. When you push brakes, then acceleration is in the opposite direction of the motion. That means that velocity will slow down. Here you see an animation that when acceleration and velocity are the same direction, the object will move faster. When acceleration and initial velocity are at the opposite direction, the object will slow down. And on the curve, acceleration is always directed toward that center of that curve, center, and then it's slowing down because it's in opposite direction of that motion. So again, you know when acceleration will increase or speed up or decrease an object. So here is an example. At the diagram A, you see that acceleration and velocity are the same direction. At the diagram D, acceleration and velocity are at the same direction. So the expected value here would be accelerating. Final velocity is going to be bigger than initial velocity. Now take a look of diagrams B and C. So either in a positive or negative doesn't really matter. What matters is the opposite of each other. So if acceleration is negative and velocity is positive, that will make the car to slow down, or other way around. If the velocity is negative and acceleration is positive, it's going to slow down anyways. So when we calculated acceleration, we found that acceleration formula is A average is equal V final minus V initial over delta t, and then you can actually solve for V final, which is a V initial plus A average times delta t, or V initial, which is V final minus A average delta t, or from an interval of time is a V final minus V initial over A average. So the velocity changes linearly at a straight line. So then in that kind of motion, we do use those formulas. We cannot use formulas if the acceleration is changing over time, which we can use graph, but we cannot use those formulas. So what we are looking for is motion with a constant acceleration, or what we are calling uniformly accelerated motion. You do the same thing with the graphs that are, if you see that the graph at graph A is getting steeper and steeper, so that means that object is accelerating. So other one is negative, but is still getting steeper and steeper. That means that both objects at the graph A and the graph B are speeding up. On this pair of graphs, so you see the tangent is positive, but it's getting less steep. That means is slowing down. So velocity is positive, acceleration has to be negative in order for the final velocity to be smaller than initial velocity. So is slowing down, positive velocity, negative acceleration. And other one actually is negative velocity because it's going down, but it's getting less steep, still negative, but less. So that means since the velocity is positive, has to be in the opposite direction, which is negative. So that's about it. This is how you can interpret the graphs on position time graph for velocity and acceleration. By looking at it, you can determine what kind of motion is happening in this graph. And that is section 1.3. Thank you. Acceleration time graph, as any graph that we learned before as a position time graph or velocity time graph, it has time in horizontal axis on x-axis, while in a vertical axis on a y-axis has acceleration. Area under the acceleration time graph, which is a multiplication of length and width, which is time and acceleration, represent change in velocity. And that's something that I need to emphasize. It's not a velocity, it is a change in velocity. We're going to focus here in a relationship between linear motion graphs. We already learned about position time graph, velocity time graph, and acceleration time graph. So graphical analysis is one of the most powerful analytical tools available to physicists. In studying the motion of the object, analyzing position time graph, velocity time graph, and acceleration time graph can help us to gain insight into a real-life event. So by looking those graphs, we know exactly how the object is moving and how we can change that motion to match what we expect that object to behave. So here is a position time graph and its accelerated motion. We already learned about how can we derive velocity time graph from position time graph, and how can derive a velocity time graph from acceleration time graph from position time graph. So those three graphs, position time graph, velocity time graph, and acceleration time graph, represent the same type of motion, uniformly accelerated motion. All three graphs look very different because they have different variables on a y-axis, so position, velocity, and acceleration. However, time on a horizontal axis has to be the same because describe the same motion that already happened in time, but seen from a different point of view, from a position point of view, from velocity point of view, or from acceleration point of view. Time has to be the same. You can derive one graph from another by taking slope of the line or by calculating area under the graph. So take a look. If you want to derive velocity time graph from position time graph, you take a slope of the line. Same way, if you want to derive acceleration time graph from velocity time graph, you take a slope of that line. However, if you want to go backward from acceleration time graph to a velocity time graph, you can calculate the area under the line, area under the graph. Same way is if you want to go from a velocity time graph to a position time graph, you can calculate area under the graph, that area under the line here. That will be enough to calculate and build that position time graph from velocity time graph. As we already mentioned, position time graph, velocity time graph, and acceleration time graph are interconnected. You can derive one graph from another by either calculating area under the line or taking the slope. Here is an example when we can derive another graph by calculating area under the line. We can create a velocity time graph by calculating area under acceleration time graph. Here is the graph, and we can try to calculate that area under that line for each second. For example, 1 second times 4 meters per second square is 4 meters per second. And another one is going to be another 4, which make 8. Another second is going to be another 4 meters per second, which is going to be 12, 16, 20. So we can build a table of value. And then by looking at those values, for time 0, we have a point 0. For time 1 second, we have 4. For time 2 seconds, we have 8, 12, 16, and 20, and so on and so forth. So we can build the data, but remember, time has to match perfectly because it's the same object moving at the same type of motion. Now, how can we express it differently is by plotting those points. So 0, 4, 8, 12, 16, 20. You draw a line, and that will be a velocity time graph that is derived by acceleration time graph. Another way to derive a graph from the other is by taking the slope of the line. And we have seen that when we analyze acceleration. So if we have a velocity time graph, then we have to derive acceleration time graph. We can take a slope of that line. Then you can calculate the slope, which is that change in velocity over interval of time, which actually is acceleration. So you can calculate the slope, change in velocity for interval of time. Change in velocity is from 0 to 7.8. You can read that from the graph. And then over interval of time is from 0 to 3. Then you can calculate that slope, which is 2.6 meters per second square, which represent acceleration. So the slope of the straight line is a constant, and the way how you draw a constant is by drawing a horizontal line at a 2.6. So one more time on a horizontal axis has to match, because we're talking about the same motion expressed in two different graphs, from velocity time graph and acceleration time graph. So time has to match. In an accelerated motion, a position time graph looks like a curve, a parabola. We already have seen that before in the previous lesson. So in order to derive a velocity time graph from position time graph in a graph that is not a straight line, what we do is you calculate the slope of the tangent on different points. For example, we have 0, 3, and 7. You don't need to do a 0 because a 0 is a horizontal line. Slope at the 0 is a horizontal line, and slope of the horizontal line is 0. So that's easy. Then you draw a line that actually touches the graph at a point 3 seconds, and then you can calculate the slope by taking 2 points. I already explained that before, and calculating the slope of the line, which is 125, which is for 9 seconds, minus 25, which is for value for 3 seconds, divided by 9 minus 3, and that you have a value of 16.7 meters per second. You do the same thing for a 0.7 second. You draw a tangent, then you can pick 2 points in the tangent that you can really easily read the value on that. So for 7 is 150 and for 4 is 25. So you can calculate that slope, 150 minus 25 over 7 minus 4, which will give you 41.7 meter per second, which you can plot. And the next step would be plotting those values. So now you have a data from a time 0, velocity 0, time 3 second, velocity is 16.7, and time 7, velocity is 41.7. So we have those 3 points. You can draw a line of the best fit, then calculate the slope of that line. The slope of that line, you can just pick 2 points there, from 0 to 3, or from 0 to 7, or from 3 to 7. Which one actually, since that is a line of best fit, that might be slightly different from those values that you can calculate. However, I already calculated it, and that is for that line that I already draw, and the slope of that line, which represent acceleration, is 5.63 meter per second square west. And then you draw a horizontal line at a 5.63 meter per second square, which is acceleration time graph. Okay, sometimes you have just a graph. How can we determine those position, velocity, acceleration from different graphs? You can just read information from a graph. You can take a slope of the line and you can find the area under the line based on what is given to you and what you want to determine. And I'm going to just give you a summary of what you need for each of those quantities. For example, if you have a position time graph and you want to determine position, so that means you can read it from a graph. It's there. But if you have a position time graph and you want to determine velocity, that means you have to take a slope of that line. If you have a velocity time graph and you want to determine velocity, again, velocity and velocity, you just read it from a graph. And if you have acceleration time graph and you want to determine the velocity or change in velocity, for this matter, you can find the area under the line under the graph. Another one is if you have a velocity time graph, the reverse now. If you have a velocity time graph and you want to find acceleration, then you can take a slope of that line. Finally, if you have acceleration time graph and you want to read and determine acceleration, it's very simple. Acceleration, acceleration. So just read it. Read the value from the graph. That's about it, all about graphs that you need to know in kinematics. So most of the information that we actually went through and learned, we did learn on section 1.2 or 1.3, but it was a good summary of everything that you need to do or to know about graphs. I hope you enjoy it. Thank you.